camera's always like, really a math person had to get me? What can a National Geographic person give me? Okay. Too bad. Okay. How do I do this? Oh yeah, purple's bad. So I get 2 integral 0 to r pi r squared minus pi x squared dx. What is pi r squared in this context? It is just a constant. So what's its integral? What's the integral of 4 dx? What's the integral of 4 dx? 4x. So it's the integral of number dx. Number x. Okay? Pi r squared is a constant. So how do you integrate? Just tack an x on the damn thing, right? And then what's the integral of this? I like it. And from 0 to r? All right, keep going. Finish that out. Yes? Where'd the negative where? Oh, it's an equal sign, sorry. Thank you. Get excited my bars get close. Or I get close to bars. Yeah, just plug it in, yeah. You should get something that hopefully looks very familiar if you can handle fractions. You should get something that looks very familiar. So when I plug a 0 in, of course it's not going to match. I don't have to worry about it. So I'm going to get pi r cubed. Is that cool? And throw an r in. Throw an r in, I get minus 1/3 pi r cubed. What's a whole pi r cubed minus a third pi r cubed? 2/3 pi r cubed. And then when I multiply by 2, you get 4/3 pi r cubed, which, if you don't know what the volume of a sphere is, that's very anticlimactic. But if you do, it's like, oh shit, there you go. That's the volume of a sphere. That's how you get it. So before today, you were just told what the shit it was. It's what it is. What? Shut up. And now you see why it is what it is. So this is related to engineering in a way, because very often in engineering you have the shape and then you rotate it to create some kind of a artwork or whatever. So if you need it to be a certain volume, or you want to figure out what volume it would be afterwards, how much water could this weird shaped fountain hold that this weird rich dude wants me to make, right? This is how you do it. You have to do calculus to figure out how much it could hold, whatever the shape is going to be. So what can I do what we just did? What can I do it for? Any shape that I then rotate. Because if I take a shape and I rotate it, when I cut it, those are going to be circles. I don't care what the shit the shape is. So if I have some arbitrary shape, let's just have it sit in the first. Right, that's the sound it makes. If I rotate that around the x-axis, I rotate that. Oh my God. Are you really going to try this, Jeff? Ah, shit. But anyway, you keep going. All right. I did this side pretty well. Any cross section I take is going to be a frickin' circle, right? What is the radius of that circle going to be? Yeah, y. So f of x, right? So then how do I find the volume of the thing? I do pi times the integral of f of x squared from whatever to whatever. Because what's pi r squared? Area of the frickin' circle across section, right? And if I integrate, I end up with the volume. Isn't that cool? Now, a slightly different way to look at this is, where is dx on this? And you don't have to look at it this way to develop this idea, but let me throw this in because it becomes really important really soon. Where is dx on this shit? Well, dx would be a little tiny step, right? A little tiny step. So then I would get this. Then I get that disk I was talking about. So to be honest, if you look at it like this, pi r squared dx, that is a volume element. Because it's the thickness times the area. That's the volume of that little disk. So if I add up all the volumes, I get the total volume. That's kind of a slightly different way to look at what we're doing. It doesn't change the work. Maybe? Maybe? I really want you... Is everybody cool with the fact that I don't care what the function looks like. If I rotate it, I end up with cross-sectional areas that are circles. Therefore, the work we did for a nice shape like a sphere is the same, even if it's a disgusting shape. Poor little shape. Okay, so let's try some of these shapes out. Let's see. I got some examples. I got a little handout. It's one of my most colorful handouts I have ever made. So you'll see that in a minute. Let's do this. I like this. Let's do this example. Blah, 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 blah. Okay. So the region, rotate the region bounded by. What you got, Jeff? Y equals square root of x. X equals 1. Y equals 0. Around the x-axis. So I really want you to understand, you never have to draw the 3D rotation. You just draw the 2D shape that will be rotated. You can do all the work you need on that. What is the main work you need to do? Let me tell, what's the most important thing to figure out? What the radius is, right? And then you got to figure out what the endpoints are, but those are normally given to you. So if you draw, did I ask you to do it? Sketch your graph? Sketch this real quick. Y equals 0 is a definition of the x-axis. I like it. It's a little extreme, but it doesn't really flatten out up there, but sure. I'm not going to be able to handle it. So here's the middle of the wall, right? So there's all my walls. X-axis, function, and then x equals 1. So that's the region. Now in section 6.1, they would ask you to find the area. Section 6.2, they're going to ask you to find the volume if you rotate it. Notice something. If I say this, let's see if it makes sense. Does that function, does that area, does this region hug the axis I'm rotating around? Yes, I love it. You guys get that idea, right? If I was rotating this region around the y-axis, oh yeah, somebody knows what's coming. If I rotate this around the y-axis, won't it have a hollow interior? Which means I'd have to cut that out, which mathematically means I'd have to subtract it. I call it a cookie cutter problem. Cut the cookie, take it out. You got a hole there, right? This is a 3D version of cookie cutter problem, but I won't. That's not what's happening yet. We're about to do that, but not yet. So this is hugging the axis I'm rotating around. I don't have to worry about some inner radius then. This is officially called a washer problem. No, I'm sorry, a disk problem. The one with the radius, inner radius is going to be a washer. Does everybody know what a washer looks like? Got a little hole in the middle so you can actually put it over stuff. I like it. Okay, so I don't have to draw any 3D shit at all. The minute I sketch my graph, what am I going to do? Integral of d what? What do you think? What kind of makes sense here? Dx. Because everything's in terms of x. This is y equals square root of x. And I don't have any, like here, if I did dy, I'd have like a lower and an upper. I don't want to do that shit. Right? And we'll get into another reason why I don't want to do it that way later. So I want dx. So what's x going from to? 0 to 1. I'll put a pi. Why can I put the pi outside? Because it's just a constant. And inside is going to be what the radius is squared. And so here's how you do the radius. So I'm moving along the x-axis, right? So for some arbitrary x value, how long is this? Be more specific. Not just y, but what is y? So for some value of x, how long is that? The square root of x. And what is that? That is the radius, right? That's the radius. So you don't have to draw this weird shit, but can you see now that's the radius of that circle? You know, pretend like it's a circle. So now what do I put inside here then? Square root of x squared, because the formula for the area of the circle is pi r squared. You don't have to draw 3D. You don't have to think necessarily 3D. You can do everything in 2D. But what that integral represents is a 3D idea. It's representing a volume. In calculus 3, you would do double and triple integrals, which more directly make the idea of area and volume. But here you don't need double and triple integrals. We can do all this shit with one integral. So what's the square root of x squared? That's crazy. Integral of x is and I want to go from 0 to 1. So 0 is nothing, so I get pi over 2 would be the volume. If I rotated this region, that would be the volume. Is that kind of neat? No? All right. Now here. What was the shape I wanted to do? Where'd you go? Oh, yeah. Oh, that's on there. That's right. Perfect. So let me do this. Here it is. Okay. Oh, no. So y equals 2x. Let's do 2x. 2x, x equal to 2, and y equals 0 around the x-axis. I want to do this one very specifically because I can do the volume of this without calculus. Let's see if you catch on. We're going to do it with calculus, and then we're going to check it by using a simple geometric formula. So they draw this, y equals 2x, so 0, 2, 4, there's that part. Yeehaw. X equals 2 is right here. Y equals 0 is the x-axis. So there's my shape. There's that triangle. If I rotate that around the x-axis, what shape have I created? Cone. Cross-section of a cone is a triangle. It's kind of neat. Just think about it. If I rotate this around, let me see if I can try this. I made a cone. In fact, let's do the geometric stuff first, and then we'll check it with calculus, and then we'll know what the answer is for the calculus. What is the volume of a cone in general? Does anybody know? Yes, 1/3. And what's it cut from? It's cut from a cylinder. Right? A cone is cut from a cylinder. In math, that's called a pyramid. It's the most basic pyramid is a cone. A pyramid is take the corners, and for a circle, the corners are every point in the circle, and take them to a single point. So that is a most basic pyramid, believe it or not. You're all like, weird ass Matthew. But what's the volume of a cylinder is pi r squared h, and if I cut a cone out, I've cut 1/3 of it out. So that's the volume of a cone is 1/3. So the volume of any pyramid is 1/3 the shape it was cut out of. So what is the radius of this cone? And when I say radius of cone, it's like at the extreme. 4. So this will be 1/3 pi 4 squared. And what's the height of the cone? 2. So when we do the calculus, we should get 32 pi over 3. So if the calculus doesn't come out to that, it's not calculus' fault, it'll be our fault. So how do I set the calculus up then? So it should be this. So I'm going to do dx or dy? Dx, okay. The dy's are coming. Pi. So what's x going from to? 0 to 2. And any arbitrary x has a radius of what? 2x. Pi r squared. That is the fundamental thing we're working with. So if you set it up, you step back, make sure it falls under pi r squared, which you just wrote down. So this is relatively easy. This is 4x squared. So when you integrate, you get 4x cubed over 3, right? From 0 to 2. When you throw a 2 in there, you get 8 times 4 is 32 pi over 3, which is what we just got. Is that semi-cool at all? So when the shape is the perfect shape that we know a geometric formula for, we can check it using that geometric formula. So here, let me give you this. We're going to work with the boring side first, and then the other side, look at the feature of this. Ooh, and the other side's got colors. Don't look at that one yet. Look at this, the boring side. Okay. Oh wait, it should be on. And we gotta do all this on the board. Somebody been playing around with this shit. Alright, well. Oh, okay. It takes me a while sometimes. I love when I mess with myself. There we go. Okay. So these are just, I want to set up the area. We're going to get into what to do when it has to be dy. It's going to be a part of this. to take the sun away, but it won't go. All right. Oh, I could have done that one too. Oh, you guys can see that? So I want first sketch this region. So y equals x squared, x equals 2. Y equals 0, that's there. So is that cool? This is a remarkably important step. You cannot skip this step. I mean, it's just crazy. And I want to rotate around the x-axis. So here's the neat thing. If you're going to use this washer method, which means the cross sections are circles, if I'm rotating around the x-axis or something parallel to the x-axis, I do integral dx. If I rotate around the y-axis or something parallel to the y-axis, I do integral dy. Okay. So here I'm going around the x-axis, so I know it's going to be integral dx. This is the region I'm going to rotate. What's my radius? X squared. X squared squared. What goes outside? 5. And x is going from 0 to 2. So go ahead and do that real quick. Oh, thank you.